Hi everyone, today we will give a brief presentation on the cold mint jelly performance in different scenarios and under different temperature conditions. Mint jelly is a shear thinning fluid with continuous 3D crystalline network consisting of high methoxyl pectin molecules, obtaining water and cold solids like sugar trapped in the pores. It is used to enhance the flavors of other foods through cooking methods like heating or cooling, and the gel network can be deformed irreversibly. During processing, the liquid and solid colloidal system is affected, and some microstructure changes are observed at the macroscopic level through the experiments to mimic the scenarios in real life. All scenarios were tested to evaluate the product performance, including scooping, penetrating, pouring, and spreading at 5 degrees room temperature and 40 degrees. The microstructure differences caused by storage condition will be explained, and all the real-life mimicked scenarios will be further discussed in the presentation.
As mentioned in the first presentation, the temperature will affect the microstructure of pectin. The test is to simulate the consumer's different storage conditions. Tester instructions prefer refrigerating it after opening, and 40 degrees to obtain any changes when it is placed near heat sources. Some reports says that the relative viscosity decreased as temperature increased. This links with the results as shown by the videos. The cold sample had a sticky texture, but the hot one was a smoother fluid. It could be because the shear modulus having a complex dependence on temperature, while between 15 to 50 degrees, the behavior is typical of a true gel, and for a lower temperature, it changes to weak gels. Leaving gels to set and observe their performance, we can obviously see that they have different light scattering effects. The cold one has a lighter color and the warm one has a deep green color. The factor could be the liquid content. As the temperature decreased, the ratio of the liquid to solid will reduce due to the crystallization. Thus, the transparency of jelly would be influenced.
Normally, the customer uses knife to puncture the mint jelly from the bottle with an increased force. We use a 40-gram ruler to simulate this process with a constant force gravity. In addition, 3 different temperature mint jelly was used to test how the storage temperature affects this process. From the experiment data, the ruler spent the least time to reach the center 2 centimeters position at 5-degree jelly, and used the most time for 40-degree jelly. It shows with decreasing temperature, the ruler spent less time to reach the same position under the gravity, which means decreasing the temperature will increase the elasticity of the mint jelly. From the puncture test research, it mentions that the high methoxyl pectin has the largest gel strength than low methoxyl and low methoxyl amidated pectin. Furthermore, the high methoxyl pectin has larger Young's module at 5 degrees than 20 degrees because the increasing temperature will destroy the hydrogen bonding of high methoxyl pectin with water. This can also explain our experimental phenomena, and the recommendation is choosing your favorite texture and then deciding how to cook it.
Consumers could also use the mint jelly by pouring it directly out of the jar. As can be seen, the chilled jelly flows relatively slowly compared to the heated sample and requires a larger pouring angle. Ideally, the pouring angle should be less than 45 degrees. This scenario can be mimicked by a sliding test. Sliding test on the first presentation found that the chilled product required a minimum angle of 35 degrees for it to flow. The room temperature required an angle of 30 degrees and the heated an angle of 20 degrees. All are within the ideal range of less than 45 degrees. This trend of higher temperatures needing smaller pouring angles can be explained by lower viscosities due to changes in the microstructure. Pouring performance can also be evaluated by comparing flow velocities. 4 grams of each temperature samples were placed on the board and tilted at angles of 35 degrees and 50 degrees. A distance versus time graph was plotted to estimate the average flow velocities. For both angles, the heated mint jelly had the fastest velocity, followed by the room temperature, and lastly the chilled. This can again be explained by differences in the viscosity of each sample. In terms of product performance, the room temperature had the ideal flow velocity, where flow is slow enough to pour in a controlled manner, yet fast enough that it wouldn't take too long to pour the desired amount.
After mint jelly is taken out from the jar by scooping or pouring, it can be spread on the toast by nearly constant shear stress applied by a knife as shown in the video. A good mint jelly can be evenly and easily spread out to a thin layer without any pectin clumps, but shouldn't be too watery. The storage temperature may affect how easily it can be spread. Since it was hard to keep constant shear stress manually using a knife, a hairdryer with a flow rate of 13.3 liters per second and room temperature airflow was used instead, to mimic the constant shear rate and shear stress applied to 5 grams of mint jelly at different temperatures. The initial area was equal to the size of a 20-cent coin. The spreading areas after 30 seconds were measured using image J and were observed to decrease as the storage temperature decreased, indicating a lower storage temperature made it harder to spread evenly. This is due to the increase in viscosity at a lower temperature as the thermal energy of pectin molecules and the intermolecular distance decreased. The optimal spreading behavior is at a moderate temperature. Hence, it's recommended to keep mint jelly at room temperature for a while before consumption.
To conclude, the performance of Cole's mint jelly was evaluated in terms of storage conditions, penetrating, pouring, and spreading the product. Storage temperature greatly affected the performance in different scenarios. The mint jelly was the easiest to puncture at higher temperatures. If at room temperature, a larger force was needed to reach a depth of 2 centimeters under 5 seconds. The product had acceptable pouring angles for all storage temperatures, but had the most favorable flow velocity at room temperature. Similarly, room temperature had the optimal spreading behavior. So overall, the Cole's mint jelly performs best when at room temperature.